Consider an expanding sphere of instantaneous radius r whose total mass remains constant. The expansion is such that the instantaneous density rho remains uniform throughout the volume. The rate of fractional change in density 1 by rho d rho by dt is constant. Now the velocity at any point. We are asked to find the velocity at any point of the surface of expanding sphere, and it is proportional to. It is given that the total mass remains constant. Even though it is expanding, total mass is constant. Mass can be given as density into volume. So we can write this as rho into 4 by 3 pi r cube since it is a sphere. This is given as a constant. Okay, since 4 by 3, that is this quantity, 4 by 3 pi r cube, this quantity is a constant. This quantity is a constant, right? That is why I'm going to incorporate it in that, and we can write pi r cube is equal to k. K is any random constant. So if we differentiate this with respect to time, we'll get this as r cube into d rho by dt, d rho by dt plus 3r square rho into dr by dt. This will be equal to 0 since k is a constant. Furthermore, we can write this as r cube into d rho by dt is equal to minus 3r square rho into dr by dt is actually equal to velocity. That is, velocity is again equal to uh, 1 by rho into d rho by dt into r divided by 3. Over here, we can clearly see that this entire term is a constant. Why so? Because we have been specifically given 1 by rho d rho by dt is actually a constant k dash. That is why we can directly write v is directly proportional to r, and this is the answer.